This video is about periodicity. In the periodic table, the elements are arranged in order of increasing atomic number. There are horizontal rows in the periodic table, and these are called periods. The vertical groups, or columns, go down, and elements in the same group have similar chemical properties because they have the same number of outer shell electrons. Periodicity, therefore, is the overall repeating pattern of these properties shown across different periods in the periodic table. The periodic table can also be split into several blocks. The blocks depend on the outer electrons. So the ones on the left are the S block because they are filling the S block outer electrons. Hydrogen and helium are also S block as they are one S1 and one S2, so only have S outer electrons. The ones on the right are filling P block orbitals, so they are the P block. The transition metals in the middle fill outer D orbitals, so they are the D block. And the lanthanides and actinides down the bottom fill F, so they are the F block. So you may be asked to identify which block a particular element is from. Look at its outer electrons, depending on where they finish, that will be the particular orbitals, therefore that will be the particular block. So now we're going to have a look at the particular trends across the period. Period 2 and period 3 show similar patterns. So first looking at period 3 trends. Firstly looking at trends in electron configuration. As you go across a period, you can see that you're adding an electron each time. Therefore you fill the S orbitals, the 3 S's, then the 3 P's, so you can see that it increases at the end by 1 electron each time. We've met first ionization energy before. The trend in first ionization energy as you go across the period increases across the period with a dip between group 2 and 3 and then another dip between group 5 and 6. Make sure you're happy why that occurs. By definition then, the first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. Therefore, if you think about this in terms of explaining the trend, why it increases, that'll be because as you go across a period, the electron being removed is in the same shell, therefore will have similar shielding. There are also more protons in the nucleus, so the nuclear attraction is greater toward the outer electrons, therefore you need more energy to remove that outer electron. The next trend we're going to look at is atomic radius. Atomic radius will decrease across the period. Have a think about why. Firstly, across the period, there are the same number of shells, therefore there will be similar shielding. There are more protons in the nucleus again, so the nuclear attraction is larger, therefore the electrons will be held much more tightly. If they're held more tightly, they're brought in, therefore the atomic radius decreases. We're just going to briefly look at ionic radius. Ions are made by either losing or gaining electrons. Positive ions are smaller than their atoms will be. This is because the same number of protons are attracting fewer electrons. Therefore, if there are fewer electrons, they'll be held more tightly by the same nuclear charge. When negative ions are formed, they have gained electrons. They are larger than their atoms. Negative ions have the same number of protons, but they're attracting more electrons. Therefore, they are less tightly held, so will be larger. The next property we're going to have a look at is electronegativity. Electronegativity is the power of an atom to attract the pair of electrons in a covalent bond. So fluorine is the most electronegative element on the periodic table. Have a think about what happens as we go towards fluorine, especially across a period. What happens at the things we've been talking about, why it would be more electronegative. So, electronegativity increases across the period because as you go across the period, there are again more protons, same shell, similar shielding, therefore the pair of electrons in the covalent bond again are more strongly attracted. So across any period, when you're talking about them, you'll be talking about there are more protons in the nucleus, same shell, similar shielding, therefore how it affects that particular property. Now we're going to look at melting points and boiling points. On the graph they've drawn points for period 2 and 3. You may be asked about this graph, so do try and become a little bit familiar with it, where the points are, the explanations why, in terms of structure bonding. Okay? So have a look at period 3 in terms of melting and boiling points, how their structure bonding affect the melting and boiling point across period 3. So firstly looking at sodium and aluminium and why there's a big difference between those two. Both are giant metallic structures, both have metallic bonding. So we know within metals we have our positive metal ions surrounded by a sea of delocalized electrons, and it's that attraction that makes our metallic bond. So with sodium we have a Na+, so we have a positive charge, whereas with aluminium we have a larger charge, we have 3+ on there, so we have a larger charge. Therefore the charge on the ion increases, also the number of delocalized electrons increases, making that metallic bond much stronger. If it's much stronger, it's going to take more energy to break. So we've considered sodium and aluminium, general trend increasing there, with both melting point and boiling point. We're now going to have a look at silicon and why in particular it's so high. So this is the structure of silicon. It's bonded by very strong covalent bonds in a giant covalent lattice structure. So structure is giant covalent, bonding very strong covalent bonds, therefore those are the bonds that need to be broken if you melt it or boil it, so the boiling point is very high. Very strong covalent bonds between the Si atoms, and lots of them, so they require a lot of energy to break, therefore high melting and boiling points. Looking back at the graph again, we're now going to have a little look at the P, S and Cl, the phosphorus, sulfur and chlorine, why they're much lower, and the trend between those three also. You may recall both phosphorus, sulfur and chlorine, in particular chlorine, when we map that with the halogens, they have simple molecular structures. So the bonds that break are the intermolecular forces between the molecules. So they've got weak van der Waals forces between the molecules. finally, looking at the graph then, we're just going to have a little look at AR, which is a simple atomic on the end. It's one of the noble gases. It's got very weak van der Waals forces between atoms, therefore it's the lowest melting and boiling point. The last page summarises all the trends that we've met. You could stop the video and fill this in as a bit of a revision. So atomic radius decreases across the period. First ionisation energy increases across the period. And you can see melting point and boiling point first increase because you've got giant metallic, strong metallic bonding, then covalent, strong covalent bonding, and then they decrease again with simple moleculars and simple atomics. And electronegativity again increasing across a period.